So thank you very much for inviting me, and I will talk about what we see related to how do we build very large scale sensor-based solutions in industry, and it has some very interesting changes compared to just building one or two sensors, and how this is going to look like, and how do we get these things to work properly. I included this slide, which is the famous ARC picture on how a factory is actually look alike. So there are three axes: the supply chain, the product life cycle, and the y-axis is from the shop floor to business. And this picture was drawn in, I think, about 20 years ago, or a variation of it. But what is happening right now is that we see that factories moves from being owned by one company or to now be a situation where we have multi-stakeholders. We have a large mining company up in northern Sweden where I live, and they normally have at least 50 subcontractors on site involved in their production every day. And this will involve transfer of information. What should I do? This is also business cases. There is money flowing, all these kind of things. So this is what's going on. And if we look at these axes and break them down a little bit, we will see that there will be tons of information flow to actually get these operations working properly. Not only along, back and forth one axis, but also in between. And importantly, this goes from things, in this case a roller bearing, which will have sensors on it. This is what companies like SKF is readily working on. That one is put into a loader, this one from Volvo. That bearing will be able to tell things not only about itself, but also things about the function of the loader. There is a driver. There is a team involved as well, and that team is an organization. We will have several of these, and these organizations might also have different legal bodies, but also have different legal grounds since they come from various countries. So this is kind of scaling the situation that we have to handle. And this is exactly what industry identified themselves. This is from a roadmap from a few years ago that was developed starting with Finland, Sweden, but also involving another at least 10 countries around Europe for the process industry. And here is the factory. There is a district heating company that supplied them with heat. Here is homes and offices, which this one is supplying waste heat to. Then the products and the markets, then the raw materials. So there is already just in this a number of stakeholders, which very clearly is in the is necessary to interact with in a closer manner and in real time to really be able to optimize and make the production much simpler. So very often we talk about that this is cyber physical systems. So it's physics involved and computation and some communication. And around one of these, this is what the control people has been doing for at least the last 40 years. Well established. But what happens when we have many of these? It's quite interesting to see that now top control scientists, they are getting very prestigious grants from the European Research Council, for example, to look into how can we model multi-dimensional and multi-cyber physical systems, since all the existing models basically is thought of breaking down. And I here try to capture some of these things that we're going to see. So when we have systems of cyber physical systems, and these systems can then grow to not only 3, 4, 5, they can be 5,000, 50,000, 5 million. But these going to show properties and behaviors. And of course, these behaviors will evolve over time due to technology changes and so on. But there will also be emerging properties and behaviors that we basically cannot predict. We have a hard time to make these scenarios to indicate how this will look like in the future. And how do we handle that? If we look at what is the existing technology out there that can support us in doing this. ABB, Siemens, Schneider, Emerson, and so on, they are supplying SCADA, DCS systems. SAP is supplying ERP systems. And then we have basically one MES supplier per factory. In addition to that, we have the smart grids, the smart city people, and so on. And these guys are not talking to each other really, and each of them are having what we today call legacy systems. And yes, you can do a lot with these, but the cost for integrating all this and getting the understanding will be prohibiting very, very soon. So there is a lot of research going on to look at what are the future frameworks and platforms where we can integrate this. We have been looking at a number of these, where we looked at a number of these frameworks, platforms that is currently being discussed at conferences like this, and for example the World Forum of Internet of Things and so on, and ICON, etc. So we looked at, there are 3 of these that's primarily coming from North America, US based to a large extent. 5 areas, something pushed by the European Commission. BASIX is something pushed primarily by Germany. AUTOSAR is the automotive industry. And then there is another arrowhead where I'm particularly involved, and where a number of very, very large European projects has been supporting and building this over the last 6, 7, 8 years. And then we talk about like between 17 to 100 partners and budgets from 60, 70 to 100 million euro in each of these projects. So there is quite substantial push around this. We have here evaluated them for a number of criteria, like can they do real time, can we do a lot of runtime engineering, are they distributed or centralized, are they open source, accessibility support, and so on. But what I will discuss here is basically what we see when we have the previous picture, this one, and what are the properties we need actually to work with to understand and to be able to first of all discuss and think of these systems and what is necessary for enabling them to be usable industrially and functional industrially, robust enough on a large scale. So I started to put together a number of these kind of properties and characteristics that we can expect from when we have these large things. So first of all, things will be highly distributed, and the things that we will have there will be also very heterogeneous. They will not all talk the same protocols and the same semantics and the same ontologies, and not even the same language. Data will be spelled in various number of languages that we find on the globe. We also look forward to very large scale. So from 100,000, that's where current legacy system actually is stopping. If you go to ABB, Siemens, Schneider, and so on, they will say there is probably 5, maybe 6, 7, 8 installations on the globe which are larger than a little bit more than 100,000 IOs. They are not bigger than that. But if we then see all the projections that we see and the potential gains, we have to look further into much, much bigger numbers. If you take cell phones, they are clearly on that scale today. But that's the only technologies, and then they have agreed on very much what is the way to communicate. So 3G, 4G, 5G, this is the only type of technology where we have that scale. But going to automation and digitization, we will have a much more heterogeneous situation. We will then see a number of things, error things, mitigations, maintenance, runtime dynamics, the evolution of the functionality, scalability of these systems. How do we segment them to ensure that we can run real-time security and all those kind of things that we find necessary, not to mention safety. To reduce cost, we need self-mitigation. We need self-engineering and self-management. A lot of these things that, when we talk about autonomous cars, that's just a first step on what we're going to see in this. We also will see business models, and we will see machines making business and also transferring money in these situations. And all these multi-stakeholder things will then move us into the classical things that we already have. But all these things need to work as well, in addition to all the new ones. And I'm probably missing a number of these type of characteristics, but this is where we are moving. So we're looking into emerging and evolving architectures in this type of context. And I will discuss a little bit more in the paper. There is some lines about each of these, but I will discuss a few of them here to keep within the time limits. This is just an excerpt of on the previous list, but what's going on there? So we will look a little bit more into distributed and runtime dynamics, runtime engineering, system of systems self-engineering, and system of system business models and nanotransaction. So let me try to guide you a little bit into what we will see and what is already going on at various places out there, what people are experimenting with. So if we take distribution and runtime dynamics, people have been talking about flexible production for quite some years now. Lot size 1 and being able to produce exactly that car or Beamer or whatever for yes one customer. Just as an example here, we are working quite a bit with Volvo Trucks. They make something like between 150 and 200,000 trucks a year, and 1.4 of them are the same about every year. So they do lot size 1, and these variations can be from 2 axes to 6 axes, or just different sets of lamps or colors and all those kind of things. They do this using the existing ISA 95 approach to how you build automation systems. But when you start to analyze the situation there, it turns out that if they want to move down here a connected nut runner from one workstation to another, that's a process of 6 months and about 100k euro. And when I told that to Gestamp, who is producing steel parts to Volvo, they said that was cheap. These architectures and structure that has been built now over the last whatever, 30, 40 years. They work, but they are extremely stiff. So we are not talking about flexible automation system, but we need to go to flexible automation systems to enable this scalability that we do foresee. So what people are looking forward to is to move these things to cloud-based things and to service-oriented architectures, and where we can do things more easily in runtime compared to what is possible with the classical ISA 95 architectures for automation. I will just show you one example of what we have done together with Volvo. And in this case, we have built a decentralized and virtualized production system where the ERP system lives in one local cloud on its own. And at some point in time, it will download the production recipe of a specific truck to be produced to a virtual truck, meaning a small computer somewhere, and or a computer somewhere. And then, when this is to be started to be produced, that virtual recipe will be downloaded to a small embedded system that actually is glued to a steel bar, which is the starting of the production of a truck at one of Volvo's factories. And when that steel bar comes to a workstation, the recipe is transferred to the workstation and telling the workstation, I will be something like this. I need these holes to be drilled, I need these bolts to be put on, and then we move down the production line. And this is further even more interesting when we're going to have trucks with diesel engines, with electric engines, with batteries, or gasoline tanks, etc. And you need to handle this supply chain and the production flow, and their existing systems is not fit for that. And all these operations that is done here, they will then be moved back to what has actually been done in the specific workstation, but also that we will get the same information back to the virtual copies of this, which means that analysis can be done already during production on where are we, quality, do we meet qualities, do we meet timelines, and this is decoupled from what's actually going down at the physical production line, which means that you never disturb that. This is just one example on what people are doing to handle this distribution and runtime dynamics. Let me give another example, and this is system of systems self-engineering. If you're adding a new IoT into a system of systems solution, which is potentially replacing an already existing one, but of course much newer, much more competent, but maybe also speaking an upgraded version of the previous protocols and so on. We can make some type of theoretical models and saying, here we have something which has a protocol situation. And the receiver on this side is understanding something similar, but not exactly the same. Can we translate this? Can we, since this is still the old one, but this one is the new replaced one, can the system then introduce a translator that actually translates this without having a lot of engineers to actually write the translator recipe? And autonomous engineering, meaning that a system can on itself autonomously change or accept a new machine coming in that is not exactly speaking the same languages, and this is a huge way of reducing cost and reducing time lag. Volvo has a target of going from 6 months to something like a few hours. And in this way, we could potentially go even further than that. So what's going on there is that people are now experimenting with introducing a machine learning AI-based approaches to do the understanding between these protocols. And this is making use of metadata, both of the physics, but also of the technologies involved. Can't say that this is prime time. It's far from. But this is approaches that we see that is going on at various universities together with industry now at various places. So progress is there, and this is an area where we need to continue to work, since this is where people spend an awful amount of time, and there are engineers doing these type of things day by day, and these guys could do something more clever. Nanotransactions. This is a schema of things coming from a factory to another factory, and there are carriers. And here comes in something interesting. Payments. Can we build an automatic system that actually handles payments? Checking that we can guarantee that things have been done. This guarantee can be built by trusted logs, meaning blockchains. And then we can also build payments systems. And this is now things which is currently published on how you do this and how do you do the negotiation and where you have acceptance and how we can build these kind of things. Next part is how do we do engineering? Current engineering is design time. And there are standardized ways of how to do this in 4 steps. And they always then need some reiteration. But if we're going to do runtime engineering as well, we probably need to add things like maintenance, evolution, and training and education for personnel as well involved here. And we will also look forward to tool chains that are integrated together and which can do a lot of these things on their own. So self-engineering, going back to my previous example. And this is runtime engineering approaches. And if we then look at having a number of these engineering stations, we potentially also can look at automated system of system engineering. When we are looking at these functionalities for production, but engineering of the automation at the same time, how do we manage and supervise these? Can we do this by rule-based? I don't think so. We can never foresee all the scenarios that will happen, and particularly not with very large-scale stuff. Sorry. The approach we are playing with now is policy-based. That we create policies for how these type of systems should be behaving. For example, a system of systems shall be stable at all levels. So we need to detect that locally and prevent unstable behavior. And we also need to monitor escalation at certain levels in these type of, since there will be hierarchies. Another example, shall be safe. And that will, for example, need monitoring security and managing of security policies. But this also implicates that policies, that these system of systems have to be agnostic to any policy changes. So policy changes should not introduce unpredictable behavior on its own. And this then starts to be very complicated. So let me conclude. We foresee that these IoTs, they need to be capable of understanding policies and behave according to policies. This is not where we are today. This is very much should do this, rule-based. System of systems, they will also need to be able to do a lot of these things, and there will be policy-driven management, for example, around this. But all these business models and nano-payments need to be part of this. And when we then look at system of system engineering, we need to understand that there will be evolutionary behavior, we will have automated engineering, all these multidimensional policy engineering and managing strategies and related policies is additional parts of this. So all in all, policy and strategy-driven IoTs and system of systems is a very open field, but also a field where we need to spend time in the future. Otherwise, a lot of the promises that the market people is talking about will never come through. So that concludes my talk. Thank you very much for listening.